Welcome. My name is Kamil Karkowski, and I'm a master's student in computer science at Tufts University. Today, I'll be giving a talk on amplitude amplification, which is a generalization of Grover's algorithm with wide-reaching implications for general computational complexity theory and practical applications for quantum computers across a wide variety of problems in multiple computer science disciplines. Without further ado, we'll start by discussing what exactly is the unstructured search problem targeted by Grover's algorithm, as well as what benefits does amplitude amplification provide over classical methods. The unstructured search problem can be phrased as follows. Given an unordered collection of objects, we are looking to identify some subset of interest. For example, we have some boxes in which a box may either contain a red ball or a green ball, and we are looking to identify all the boxes containing green balls. Now, in the scenario that we've set up here, what would the optimal strategy for finding the single green ball in the 10 boxes look like? Pause the video now to give yourself a chance if you'd like to come up with an answer yourself. The answer is, classically, we'd have to investigate, on average, half of all of the boxes involved. There is no better strategy than sequential guess and check, as we have no external information provided. In the quantum case, the interesting phenomenon with Grover's algorithm is we only have to apply Grover's algorithm 3 times a square root of the total number of boxes to achieve a high probability coverage that we find the green ball. To help cover the exact practical implications of this quadratic speedup and what that entails, we'll briefly cover computational runtime complexity. Big O notation runtime complexity seeks to capture algorithm runtime as a function of the size of the input space. In our example, we have n boxes, and here the blue line represents an ON linear algorithm, the best classical option scaling with the number of boxes. The red line represents square root n, the runtime in terms of Grover's algorithm iterations for the unstructured search problem. We see that big O notation runtime benefits scale as a function of n, where we can imagine if we have 1 million boxes, the classical operation requires 500,000 operations, while the Grover's algorithm runtime will require a constant multiple of 1,000 Grover algorithm iterations. On to amplitude amplification. The algorithm is a generalization for search problems in which we may have more than one correct answer. Search problems with multiple correct answers are more practical for real-life applications, and strictly speaking, they're slightly easier mathematically as partial matches or otherwise can be obtained in the space. However, this requires a more thorough and complex framework in order to implement the circuit involved. So let's go into explaining how superposition achieves this quadratic speedup over the search space. Classically, we can do a single forward calculation for a single input at a given time. In the quantum scenario, what we can do is take a superposition of possible input states over the qubits and apply the forward function across all members of the superposition in a single forward step, yielding an output which is also superposition relative to all those inputs. This gets us started somewhere interesting, and we apply a further refinement algorithm to shift probability mass into the desired subspace. This refinement algorithm consists of 2 operators applied sequentially. The process repeatedly applies those 2 operators a square root n a number of times. And the final result will be such that when measured has a high probabilistic likelihood of yielding answers belonging to the correct subspace we mentioned before. For practical applications considerations, we'll consider the 10-box example and set up a quantum oracle function for that. You can think of the function as inducing a bit flip when an input is the search target in our search space. On a quantum example, you can imagine is when we apply a qubit corresponding to the index of the box we're looking for, we phase flip that qubit. So we define this quantum oracle function where f of x is equal to negative x state, for x is equal to indices represented by boxes 2 and 5. As the initial input to our function, we start with a uniform superposition of the first 10 numbers. These correspond to our 10 boxes of interest that we are searching. We can toss away the last 6 integers in Z16, as our oracle function guarantees that they do not correspond to boxes containing the green ball. This brings us to a point about amplitude amplification and Grover's algorithm. You don't have to start with a pure uniform superposition of all possible inputs if there are some boundary conditions or heuristics on the function domain such that you expect the correct answers to lie in some subregion. Thus, the steps of the algorithm are as follows. We set up the initial state, the superposition of the first 10 box indices. And here we have a graphical representation of these associated amplitudes. We apply the quantum oracle function, which phase flips indices 2 and 5. Next up, we discuss what the graphical interpretation of the diffusion operator is. We see that the diffusion operator inverts the probability mass element-wise about the total probability mass mean. And what this does is, since we phase flipped the desired search space elements, the result is that the amplitude associated with the desired elements is increased, while the amplitude associated with undesirable elements is uniformly decreased. So what I did was I went forward and implemented the amplitude amplification algorithm, these multiple correct answers, using this quantum oracle. I found some interesting results I'd like to share with you now. We noticed that while we initially set the probability masses associated with indices 11 through 16 of our boxes to 0, a single iteration of amplitude amplification will actually amplify those probabilities to a very high non-zero value, higher than the other bad answers, lower than the correct answers we actually are searching for. This brings up an interesting point. If we have constraints on our search space, but we naively just apply them to the algorithm, those answers will reintroduce themselves in this diffusion operator step. Although over time, asymptotically, they are being reduced, and the likelihood of getting the answers that we want is asymptotically very high. It was very interesting to apply the diffusion operator to a non-strictly uniform superposition of inputs. And there were some technical challenges involved. Specifically, debugging was much more difficult, as looking at the probability distribution initially threw me for a shock, as I didn't expect this behavior of amplifying the zero probability states with the diffusion operator. So what are all the implications of this, and why do we really care about this problem? One of the key things I'm personally interested in, as somebody who studies machine learning, is when you're doing the machine learning model fitting process, you can treat parameter selection as a form of unstructured search over your search space. So in fact, any optimization problem can benefit from a quadratic speedup using amplitude amplification. This allows us to either have a quadratic speedup in the execution of that algorithm, or double the number of parameters, causing a quadratic increase in the search space, while maintaining the same performance as an analogous classical solution. Now, of course, there's applications to cryptography as well. Those aren't as popular, not so much talked about. One of the key things being is a quadratic speedup doesn't break a lot of cryptographic protocols. Reason for that being is we can double token length, which is a quadratic increase in the number of possible passwords that can be cracked, to counter the quadratic speedup of amplitude amplification in general Grover's algorithm. This does mean you can use Grover's algorithm or amplitude amplification to crack a longer length of passwords. However, that just sort of shifts the problem into third-party authentication and the like, where consumers store long passwords on keychains. The notation for the diffusion operator at an initial glance can be a little bit confusing. It's described as an outer product doubled subtracted with an identity operation. What exactly does that mean? I've provided an algebraic proof showing how this exact formulation corresponds to this inversion about the mean function that we're interested in, that we can think of as an element-wise operation. This gets into what are householder transformations or householder matrices, but I found this to be a useful exercise to show the algebraic link between those transformations and the geometric interpretation of this inversion that we're working with.